All right, let's talk about something that's both fascinating and, let's be honest, a bit mysterious. Boltzmann machines. If you've ever wondered how machines learn patterns, generate new data, or even make decisions without explicit programming, you're in for a treat. We're about to explore the inner workings of Boltzmann machines, from their structure to their decision-making abilities and their role in generative models. Think of them like a secret society of neurons, all talking to each other, exchanging information, and figuring things out probabilistically. Sounds cool, right? Well, it gets even better. We'll start with a bit of history, how Boltzmann machines evolved and how key figures like Geoffrey Hinton transformed them into powerful tools for deep learning. Then we'll break down their architecture, their ability to learn from data distributions, and why their stochastic decision-making sets them apart from conventional neural networks. And just when you think you've got the basics, we'll take things further. We'll compare Boltzmann machines with other models, see how they're trained with contrastive divergence, and explore their strengths, weaknesses, and opportunities for improvement. Along the way, we'll uncover their real-world applications, think recommendation systems, natural language processing, and even image recognition. But here's the kicker. Despite their power, Boltzmann machines are not without challenges. So the real question is, where do they fit in today's AI landscape? Do they hold the key to the future of deep learning, or are they a hidden gem waiting for rediscovery? Stick with me, and by the time we hit that final slide, you'll not only understand Boltzmann machines, you might just start seeing them everywhere. Ready? Let's dive in. All right, let's talk about Boltzmann machines, one of the most fascinating yet underrated concepts in machine learning. These aren't your typical neural networks. Instead of just taking input, processing it, and giving an output like a well-behaved algorithm, they take a completely different approach. They think in probabilities, they explore, they adjust, and most intriguingly, they generate. At their core, Boltzmann machines are all about learning patterns in data. But instead of following a rigid set of rules, they rely on a concept called stochasticity, meaning they make decisions by sampling from a probability distribution. It's like throwing a dice, but with intelligence. This makes them incredibly powerful for tasks like feature learning, recommendation systems, and even generating new data from scratch. What makes them special? Unlike traditional neural networks, every neuron in a Boltzmann machine is connected to every other neuron. This allows them to discover deep relationships in data without needing labels, making them excellent for unsupervised learning. In fact, they've played a huge role in the development of modern deep learning architectures like Restricted Boltzmann Machines, RBMs, and deep belief networks, DBNs, which are key players in feature extraction and representation learning. But here's the catch. Training them isn't easy. They require sophisticated algorithms like contrastive divergence to adjust their weights effectively, and they can be computationally demanding. That's why they've often been overshadowed by more mainstream deep learning models. So the real question is, are Boltzmann machines an untapped resource in AI, or have they been left behind for a reason? As we explore their architecture, training methods, and applications, you'll start to see just how much potential they hold. Let's dive in. Now, let's take a step back and talk about where Boltzmann machines actually come from, because like any great innovation, they didn't just appear out of nowhere. Their story is tied to some of the biggest breakthroughs in neural networks and machine learning. It all started in 1985 when Geoffrey Hinton and David Ackley introduced the concept of Boltzmann machines. They were inspired by statistical mechanics, yes, the kind used in physics, to create a network that could learn by adjusting the interactions between neurons. Instead of simply passing signals forward like in traditional neural networks, these machines worked by balancing probabilities, constantly adjusting and refining their internal states to make better predictions. Fast forward to 1986, and we see Boltzmann machines being recognized as powerful tools for learning representations, thanks to Hinton's groundbreaking paper on backpropagation. But there was a problem. Training them was painfully slow. They needed a better way to adjust weights efficiently. In 1992, things started changing when researchers introduced contrastive divergence, a method to speed up training. And then came the real game changer. In 2006, deep belief networks, DBNs, took the machine learning world by storm. These networks were built on stacked layers of restricted Boltzmann machines, RBMs, a simplified version of Boltzmann machines. Suddenly, what once seemed like a theoretical curiosity became a practical tool for deep learning. So, why does all of this matter? Because history tells us that ideas often come before their time. Boltzmann machines may have taken a back seat in the deep learning revolution, but their influence is still everywhere, hidden in the architecture of modern AI. And as computing power grows, who's to say they won't make a major comeback? Now that we've seen where they came from, let's look at how they actually work. Get ready, because this is where things start getting really interesting. Now that we understand where Boltzmann machines come from, let's break down how they are actually built, because their structure is what makes them both powerful and, at times, challenging to work with. Unlike traditional neural networks, where data flows in a specific direction, Boltzmann machines operate differently. Every neuron in the network is connected to every other neuron, and these connections are bidirectional. This means information isn't just moving forward like in a feed-forward neural network, it's constantly flowing back and forth, adjusting and refining itself. Think of it like a group of people having a conversation where everyone is talking to everyone else, exchanging ideas until they reach a consensus. A Boltzmann machine consists of two main layers. The visible layer is where input data enters the system. This is what we can observe directly, much like the features in a dataset. Pixels in an image, words in a sentence, or user interactions in a recommendation system. Then there's the hidden layer, which is where the real learning happens. The hidden neurons don't receive input directly from the outside world. Instead, they interact with both the visible neurons and each other, gradually uncovering deeper relationships and structures within the data. These hidden layers allow the model to capture complex patterns that might not be immediately obvious. What makes Boltzmann machines truly unique is the way they learn. Every connection between neurons has a weight, and these weights determine the strength of interaction between them. The machine doesn't just memorize input like a rigid algorithm, it continuously updates these weights based on probabilities, refining its internal structure to better understand the data. This process allows it to learn the underlying distribution of the input rather than just mapping inputs to outputs like traditional neural networks. However, because every neuron is connected to every other neuron, training can be computationally expensive and time-consuming. Unlike more structured architectures where information flows in a controlled manner, Boltzmann machines work by exploring different states and adjusting their connections dynamically. One of the key challenges with Boltzmann machines is that they treat all neurons equally. There's no clear distinction between input and output neurons, which can make training inefficient. To address this, a more efficient variation called the Restricted Boltzmann Machine, or RBM, was introduced. Unlike standard Boltzmann machines, RBMs impose restrictions on how neurons connect. Visible neurons only connect to hidden neurons, not to each other. This simplification makes training significantly faster and allows RBMs to be stacked into deeper models, leading to powerful architectures like deep belief networks. So, what does all of this mean? Boltzmann machines are incredibly powerful because they can model complex relationships in data, making them ideal for tasks like feature learning, unsupervised clustering, and even generative modeling, but their full connectivity also makes them computationally expensive to train. The challenge is in balancing their flexibility with efficiency. Now that we understand their structure, the real question is, how do they actually learn? Because that's where the magic happens. Let's take a closer look at their decision-making process next. Now that we understand the structure of Boltzmann machines, let's talk about what makes them truly unique. Their ability to make stochastic decisions. Unlike traditional neural networks that follow strict rule-based computations, Boltzmann machines introduce randomness into the learning process. Instead of deterministically assigning outputs based on fixed calculations, they make decisions based on probabilities. This allows them to explore multiple possibilities rather than just converging to a single predefined answer. The key to this lies in the energy-based model that governs their behavior. Each configuration of neurons in a Boltzmann machine is assigned an energy value, and the network constantly tries to minimize this energy by adjusting its connections. States with lower energy are more probable, while those with higher energy are less likely. This principle is inspired by physics, specifically thermodynamics, where systems naturally evolve towards states of lower energy. But here's where it gets even more interesting. Boltzmann machines don't just learn by minimizing error like traditional networks. They explore different states using a process called stochastic sampling. Instead of immediately settling on a fixed pattern, they randomly switch between different configurations, evaluating which ones produce the most meaningful relationships in the data. This helps them escape local minima, places where learning might get stuck, and find better overall solutions. One of the most commonly used techniques for this is Gibbs sampling, where neuron states are updated iteratively based on the probabilities dictated by the network's energy function. This stochastic nature is what allows Boltzmann machines to be incredibly effective in capturing complex patterns and generating new data. Instead of merely recognizing patterns in training data, they simulate possibilities, generating predictions and outputs that reflect the learned distribution. This is why they are so valuable in generative modeling, creating new images, producing recommendations, or even synthesizing text. But this strength is also a challenge. Because they rely on randomness and probability distributions, training a Boltzmann machine can be computationally expensive. Unlike standard neural networks that update weights based on clear gradients, Boltzmann machines need to run multiple iterations of sampling before settling into an optimal state. This means more computation, longer training times, and a higher demand for processing power. Despite these challenges, their ability to model uncertainty and probabilistic relationships makes them powerful tools in many fields, from pattern recognition and collaborative filtering to generative modeling. They offer a flexible approach that deterministic models often struggle to match. Now that we understand how Boltzmann machines make decisions, the next step is figuring out how they learn from data distributions. Because while their stochastic nature is fascinating, what's even more impressive is how they refine their knowledge over time to generate even better results. Let's dive into that next. Now that we've explored how Boltzmann machines make stochastic decisions, let's talk about how they learn from data distributions. Because their true power lies in their ability to uncover hidden patterns and generate new data that resembles what they've learned. Unlike traditional machine learning models that rely on labeled datasets, Boltzmann machines can learn unsupervised, discovering underlying structures without explicit instructions. At the core of their learning process is adjusting the weights of connections between neurons. Instead of simply memorizing data, they aim to model the probability distribution of the input. This means they don't just recognize individual examples, they learn the overall characteristics of the data and can generate new instances that fit within that learned distribution. Imagine giving a Boltzmann machine thousands of handwritten digits. Instead of just classifying them as numbers, it learns the essence of what makes a 7 or a 3. and can even generate entirely new, never-before-seen, handwritten digits that still resemble the real ones. This learning process happens in two phases, a positive phase and a negative phase. In the positive phase, the model looks at real data samples and strengthens the connections between neurons that frequently activate together. In the negative phase, the model generates its own data samples by sampling from the learned distribution, and it weakens the connections that don't contribute to accurate predictions. The goal is to make the generated data as similar as possible to the real data while still exploring new possibilities. To efficiently adjust weights, Boltzmann machines use a special training algorithm called Contrastive Divergence. Instead of computing probabilities over all possible configurations, an impossible task for large datasets, Contrastive Divergence speeds up learning by focusing only on a small number of updates at a time. It alternates between real data and generated data, refining the network's weights in small steps. This makes training significantly faster while still allowing the model to approximate complex distributions. But here's the catch. Because Boltzmann machines operate probabilistically, training them is computationally demanding. Unlike traditional neural networks, where weights are updated based on direct error calculations, Boltzmann machines rely on iterative sampling to adjust their parameters. This means they need more time and computational power to learn effectively. This is one reason why restricted Boltzmann machines, RBMs, became more popular. They impose structural restrictions that make training much more efficient. Despite these challenges, the ability of Boltzmann machines to model real-world distributions and generate new data makes them incredibly valuable in many applications. From recommendation systems to generative models for images and text, they offer a unique approach that allows AI to go beyond simple classification and actually create new, meaningful data. Now that we've seen how they learn, let's take things a step further. What happens when we use Boltzmann machines as generative models, where they don't just learn patterns, but actually generate new data from scratch? That's where things get even more exciting. Let's explore that next. Now that we understand how Boltzmann machines learn from data distributions, let's talk about their role as generative models. Unlike traditional machine learning models that simply classify data, generative models take things a step further. They learn the underlying patterns in data and then create new data that looks just like it. Instead of just recognizing a cat in an image, a generative model can generate entirely new cat images that never existed before. This ability makes generative models incredibly powerful in fields like image synthesis, text generation, and even AI-driven creativity. So how do Boltzmann machines fit into this? They learn by adjusting their weights until they capture the full probability distribution of the training data. Once trained, they can generate new samples by sampling from that learned distribution. Think of it like an artist who has studied thousands of paintings and can now create a completely original piece in the same style. The Boltzmann machine doesn't just memorize specific examples, it understands the overall characteristics of the data and can produce new instances that belong to the same pattern. This is what sets generative models apart from discriminative models, which focus only on drawing boundaries between categories. A discriminative model looks at data and tries to answer questions like, is this an apple or an orange? A generative model, on the other hand, asks, what does an apple actually look like? And then creates an entirely new apple from scratch. One of the most famous applications of generative models is in deep learning, where they power things like deepfake technology, AI-generated art, and even music composition. In fact, some of the earliest breakthroughs in deep learning, like deep belief networks, DBNs, were built on top of restricted Boltzmann machines, RBMs, a special type of Boltzmann machine designed for efficient training. But as powerful as they are, generative models based on Boltzmann machines come with challenges. Training them can be slow, requiring multiple iterations of sampling to refine their probability distributions. They also require careful tuning of parameters to ensure that they generate high-quality samples rather than random noise. Despite these hurdles, their ability to simulate reality makes them an essential tool in artificial intelligence, whether it's generating realistic human faces, predicting missing data in medical research, or creating personalized recommendations. Generative models help machines go beyond simple classification and actually create something new. Now that we've seen how Boltzmann machines function as generative models, let's take a deeper dive into how they compare with discriminative models. Because while both have their strengths, understanding the difference is key to knowing when to use one over the other. Let's break it down next. Now that we've explored how Boltzmann machines function as generative models, it's time to compare them with discriminative models. This is one of the most important distinctions in machine learning, and understanding the difference between these two approaches is crucial for knowing when and where to use each one. Think of it like this. A discriminative model is like a detective trying to figure out if someone is guilty or innocent based on evidence. It looks at the available features, finds patterns, and draws a decision boundary between different categories. A generative model, on the other hand, is more like a novelist. It doesn't just classify things. It learns the underlying structure and can generate completely new instances that fit within the data distribution. So, how does this apply to Boltzmann machines? They fall into the generative model category, meaning they don't just learn to separate categories, but they learn the entire probability distribution of the data. This allows them to generate new data points, making them useful for applications like image generation, recommendation systems, and unsupervised feature learning. Discriminative models, on the other hand, focus purely on prediction and classification. They work by mapping input features directly to output labels, making them ideal for tasks like spam detection, fraud detection, or sentiment analysis. Popular discriminative models include logistic regression, support vector machines, SVMs, and deep learning models like convolutional neural networks, CNNs, that classify images. To make the comparison even clearer, let's consider an example. Imagine you have a data set of emails, some labeled as spam and others as not spam. A discriminative model would look at the words in each email, identify key features like free money or urgent, and draw a decision boundary between spam and non-spam messages. A generative model, like a Boltzmann machine, wouldn't just classify emails, it would learn the overall structure of emails and could even generate a completely new email that resembles the real ones. Because generative models learn a deeper representation of data, they are especially powerful for unsupervised learning, where there are no predefined labels. They can discover hidden patterns, generate missing values in datasets, and even create entirely new content. However, they are often slower to train and require more computational resources compared to discriminative models. So, when should you use each one? If your goal is to classify data efficiently and accurately, a discriminative model is usually the best choice. But if you need to model the underlying structure of data, generate new instances, or work in an unsupervised learning setting, then a generative model like a Boltzmann machine is the way to go. Now that we've covered the key differences, let's take a closer look at the strengths of Boltzmann machines and why they continue to be relevant despite their computational challenges. Because while they might not always be the fastest, their unique ability to uncover deep patterns in data makes them a powerful tool in machine learning. Let's explore that next. Now that we've seen how Boltzmann machines differ from discriminative models, Let's dive into their strengths, because while they may not be the most widely used models today, their unique abilities make them incredibly powerful in the right contexts. One of their biggest strengths is their ability to learn complex probability distributions. Unlike traditional neural networks that focus on direct input-to-output mapping, Boltzmann machines capture intricate relationships between variables, allowing them to model complex dependencies in data. This makes them especially useful for unsupervised learning, where there are no predefined labels and the model has to uncover hidden structures on its own. Another major advantage is that they can learn from both labeled and unlabeled data. Most machine learning models rely heavily on labeled datasets, which can be expensive and time-consuming to create. Boltzmann machines, on the other hand, excel at finding patterns even when labels aren't available, making them valuable for tasks like feature learning, clustering, and dimensionality reduction. Their flexible architecture also makes them adaptable to various applications. Because they are built on an energy-based model, they can be fine-tuned to work with different types of data, from images and text to recommendation systems. This is why restricted Boltzmann machines, RBMs, became so popular in deep learning. By simplifying connections, RBMs made training more efficient while preserving the power of Boltzmann machines for learning deep representations. One of the most fascinating strengths of Boltzmann machines comes from their theoretical foundation in statistical mechanics. Unlike conventional neural networks, which rely purely on backpropagation, Boltzmann machines use principles from physics, specifically thermodynamics, to guide their learning process. By minimizing energy states and balancing probability distributions, they create models that are not only powerful but also conceptually elegant. These strengths make Boltzmann machines particularly useful in fields like generative modeling, collaborative filtering, and anomaly detection. Their ability to discover hidden patterns makes them ideal for recommendation systems where they can predict user preferences based on past behavior. Similarly, their ability to generate realistic samples makes them valuable in image generation and deep learning feature extraction. However, despite these advantages, Boltzmann machines are not perfect. Their complexity and computational demands have limited their widespread adoption in large-scale machine learning applications. Training them is challenging, and the reliance on iterative sampling can make learning slow compared to more modern deep learning models. This leads us to an important question. What are the key weaknesses of Boltzmann machines, and how do they impact their practical use? While their theoretical power is undeniable, their real-world challenges have made them less common in mainstream AI development. In the next section, we'll take a closer look at these limitations and discuss what's being done to overcome them. While Boltzmann machines have some impressive strengths, they also come with significant weaknesses that have limited their widespread adoption. Understanding these challenges is crucial because it helps us see why they haven't become as mainstream as other neural network architectures. One of the biggest weaknesses of Boltzmann machines is their computational complexity. Unlike traditional neural networks that use straightforward gradient descent, Boltzmann machines rely on stochastic sampling techniques, such as Gibbs sampling, to update their weights. This makes training incredibly slow, especially for large data sets. Since every neuron is connected to every other neuron, the number of interactions grows exponentially as the network scales. This means training a full-scale Boltzmann machine can take an impractically long time, even on modern hardware. Another challenge is difficulty in training. Because Boltzmann machines are based on probability distributions, training them involves balancing between exploring new states and converging to useful patterns. If the sampling process isn't done correctly, the model can get stuck in poor local minima or take too long to reach an optimal state. To make matters worse, Their reliance on stochastic updates means that training results can vary significantly from one run to another, leading to inconsistent performance. A third major limitation is lack of interpretability. In many machine learning models, we can trace back decisions to specific features or understand why a model made a particular prediction. But Boltzmann machines operate in a highly distributed manner, meaning knowledge is spread across the entire network. This makes it difficult to understand exactly how the model arrived at a particular decision, which can be a major drawback in areas like finance or healthcare, where explainability is critical. Then there's the issue of scalability. The unrestricted connections between neurons in a standard Boltzmann machine make it impractical for large-scale applications. This is one of the reasons why restricted Boltzmann machines, RBMs, were introduced. By limiting the connections between visible and hidden layers, RBMs make training faster and more manageable. However, even RBMs have their limitations, and they've largely been replaced by more efficient deep learning architectures. Despite these weaknesses, researchers haven't given up on Boltzmann machines entirely. There have been significant efforts to improve training algorithms, such as using contrastive divergence to speed up learning, and some researchers are exploring ways to integrate Boltzmann machines with modern deep learning techniques. So where does this leave us? Are these weaknesses deal breakers, or are there ways to work around them? The truth is, while Boltzmann machines may not be the first choice for many modern AI applications, they still have unique opportunities for improvement that could make them more viable in the future. Let's explore what's being done to overcome these limitations and how they might still find a place in the evolving landscape of machine learning. While Boltzmann machines face significant challenges, they also present unique opportunities for improvement that could make them more practical and widely adopted in the future. Many of their limitations, slow training, high computational costs, and scalability issues, are being actively addressed through new techniques and hybrid approaches. The question is not whether Boltzmann machines are obsolete, but rather how they can be optimized and adapted for modern machine learning. One of the biggest areas of improvement is better training algorithms. Traditional Boltzmann machines rely on slow sampling techniques like Gibbs sampling, which makes learning inefficient. However, newer methods such as contrastive divergence have already sped up training significantly. Researchers are also exploring more advanced optimization techniques like persistent contrastive divergence and parallelized sampling, which allow for faster convergence and more stable learning. These improvements could make Boltzmann machines more practical for large-scale datasets. Another exciting direction is the integration of Boltzmann machines with deep learning architectures. In the early days of deep learning, restricted Boltzmann machines, RBMs, were widely used to pre-train deep networks, forming the foundation of deep belief networks, DBNs. While RBMs have largely been replaced by modern techniques like autoencoders and transformers, researchers are still investigating how energy-based models like Boltzmann machines can be combined with deep neural networks. For example, they could be used to enhance feature learning or improve generative modeling in a way that complements existing AI models. One area where Boltzmann machines still hold strong potential is in quantum computing. Because they are fundamentally based on probability distributions and energy minimization, they align well with quantum mechanics. Some researchers believe that quantum Boltzmann machines could leverage quantum computing's ability to perform massive parallel computations, drastically reducing training time. This could revive interest in Boltzmann machines for large-scale applications that are currently impractical with classical hardware. Boltzmann machines also continue to show promise in unsupervised learning and generative modeling. While they are not as widely used as generative adversarial networks, GANs, or variational autoencoders, VAEs, they still provide an alternative approach to generating synthetic data. Their ability to learn deep probabilistic representations makes them valuable in applications where uncertainty modeling is important, such as scientific simulations, anomaly detection, and probabilistic reasoning. Despite these opportunities, the reality is that Boltzmann machines still require significant improvements to become mainstream again. The field of machine learning has evolved rapidly, and newer architectures have largely taken their place. However, the principles behind Boltzmann machines, energy-based learning, probabilistic modeling, and deep representations are still influencing modern AI research in many ways. So, what does this mean for the future of Boltzmann machines? While they may not be the dominant architecture today, ongoing research into better training, hybrid models, and quantum computing could bring them back into the spotlight. Their story isn't over yet, but before we look at their long-term potential, let's consider the biggest challenges to their adoption, because despite these opportunities, there are still some major hurdles that need to be overcome. Let's explore that next. Let's explore. While Boltzmann machines present exciting opportunities for improvement, there are still significant threats to their adoption that have prevented them from becoming a dominant force in modern machine learning. Despite their theoretical strengths, practical limitations have kept them from widespread use in industry and large-scale AI applications. Understanding these obstacles is key to evaluating their future potential. One of the biggest threats is competition from more efficient deep learning models. Over the past decade, architectures like deep neural networks, convolutional neural networks, CNNs, and transformers have revolutionized AI, outperforming Boltzmann machines in almost every practical application. While Boltzmann machines were once used in feature learning and pre-training, techniques like autoencoders, GANs, and variational autoencoders, VAEs, have largely taken over this space. These newer models train faster, scale more effectively, and produce higher quality results, making it difficult for Boltzmann machines to compete. Another major challenge is computational inefficiency. Training Boltzmann machines requires repeated probabilistic sampling, which can be slow and resource intensive. Even with optimizations like contrastive divergence, they still lag behind gradient-based deep learning models that can be efficiently trained using modern GPUs. This makes them impractical for real-world applications where speed and scalability are crucial. As deep learning continues to evolve with better hardware and optimized training methods, Boltzmann machines risk being left behind. There's also the issue of lack of industry adoption. While Boltzmann machines were influential in early deep learning research, they have not been widely implemented in production environments. Tech companies and AI research labs have focused on more scalable and interpretable models, leaving Boltzmann machines as more of a niche research topic than a practical tool for large-scale machine learning projects. Without strong real-world adoption, research interest in Boltzmann machines has declined compared to other AI paradigms. Another limiting factor is difficulty in interpretability. Many businesses and industries require AI models that can explain their decisions, especially in fields like healthcare, finance, and autonomous systems. Because Boltzmann machines distribute knowledge across a network in a highly probabilistic way, it is difficult to understand why they make certain decisions. In contrast, decision trees, attention mechanisms in transformers, and other explainable AI XAI models provide clearer insights, making them preferable in sensitive applications. However, despite these challenges, Boltzmann machines are not entirely obsolete. There is ongoing research into how they can be improved, integrated with modern deep learning models, and even leveraged in new fields like quantum computing and probabilistic reasoning. Their ability to learn deep representations and generate realistic data still holds potential, if researchers can find ways to make them more efficient and scalable. So, where do we go from here? Are Boltzmann machines just a piece of machine learning history, or could they still have a place in the future of AI? To answer that, let's explore how they are being used today and where they might still make an impact in real-world applications. That's what we'll uncover next. Despite the challenges and competition from more mainstream deep learning models, Boltzmann machines still find valuable applications in various fields. Their ability to model complex probability distributions, discover hidden patterns, and generate new data makes them useful in areas where uncertainty, structure discovery, and probabilistic reasoning are key. While they may not be the go-to model for large-scale AI deployments, they still offer unique advantages in specialized applications. One of the most well-known uses of Boltzmann machines is in recommendation systems. Companies like Netflix and Amazon rely on machine learning models to suggest content to users based on their past behavior. Boltzmann machines excel at capturing subtle patterns in user-item interactions, making them useful for collaborative filtering techniques. Instead of just recommending the most popular items, they can identify deeper relationships between user preferences and products, improving personalization. While they have been largely replaced by deep learning-based recommendation algorithms, their influence on this field is undeniable. Another major application is in natural language processing, NLP. Although transformers like GPT have become the dominant models for language tasks, Boltzmann machines have been explored for text generation and language modeling. By learning the probability distribution of word sequences, they can generate new sentences that resemble human written text. This makes them useful in AI-driven content creation, automated writing, and machine translation, though they are less commonly used today due to computational inefficiencies. Boltzmann machines have also played an important role in image recognition and feature extraction. Because they can learn hierarchical representations of data, they have been used in early deep learning models for detecting patterns in images. Restricted Boltzmann machines, RBMs in particular, were used in deep belief networks, DBNs, to extract meaningful features from images before deep convolutional networks took over. While they are no longer the preferred choice, they laid the groundwork for modern deep learning techniques used in facial recognition, object detection, and medical imaging analysis. Another interesting application is in anomaly detection. Since Boltzmann machines learn the underlying structure of a data set, they can identify when a new data point deviates from the expected distribution. This makes them valuable in cybersecurity, fraud detection, and industrial monitoring, where detecting subtle irregularities is crucial for preventing attacks, financial losses, or system failures. Their ability to work in unsupervised settings makes them particularly appealing for applications where labeled data is scarce. Perhaps one of the most promising areas for Boltzmann machines is in scientific research and probabilistic modeling. They have been used in fields like physics, neuroscience, and bioinformatics to model complex systems with probabilistic dependencies. In scientific simulations, where understanding hidden relationships in large datasets is critical, Boltzmann machines can help uncover patterns that other models might overlook. Even though they are no longer at the center of deep learning innovation, their influence is still present in modern AI. Their strengths in unsupervised learning, generative modeling, and probabilistic reasoning continue to make them relevant in niche applications. But the real question is, what does the future hold for Boltzmann machines? Are they a fading piece of machine learning history, or could new advancements bring them back into the spotlight? Let's explore the future directions of Boltzmann machines and how they might evolve in the ever-changing world of AI. Training Boltzmann machines is one of the most challenging aspects of working with them, but it's also where the real power of these models comes to life. Unlike traditional neural networks that rely on straightforward backpropagation, Boltzmann machines use a probabilistic learning process to adjust their weights and uncover deep patterns in data. This makes them excellent for unsupervised learning, but it also makes training computationally expensive and complex. The first step in training a Boltzmann machine is data preparation. The quality of input data plays a huge role in how well the model performs. The data needs to be normalized, structured, and sometimes pre-processed to remove noise, ensuring that the Boltzmann machine can learn meaningful patterns rather than random fluctuations. Once the data is ready, the next step is defining the energy function, which is at the heart of how Boltzmann machines learn. The energy function determines how neurons interact and how likely certain configurations of neurons are to appear. By tweaking the weights of connections between neurons, the machine minimizes the energy of the system, allowing it to converge on patterns that best represent the data. The real challenge in training comes from the fact that Boltzmann machines don't just update weights directly based on errors, as in conventional deep learning models. Instead, they use contrastive divergence, an iterative algorithm that trains the model by alternating between real and generated data. The model learns by adjusting its parameters so that its generated data looks more and more like the real data over time. Contrastive divergence works in two phases, a positive phase and a negative phase. In the positive phase, the model looks at real-world data and strengthens the connections between neurons that frequently activate together. In the negative phase, the model generates its own sample data and weakens connections that don't contribute to accurate predictions. This back-and-forth process allows the model to gradually refine its weights, but it can take many iterations to achieve good results. One of the biggest challenges in training Boltzmann machines is the need for stochastic sampling. Because the model operates probabilistically, it requires methods like Gibbs sampling to explore different states before making adjustments. This makes training computationally expensive, especially for large data sets, as it requires repeated simulations to fine-tune the probability distribution. This is why restricted Boltzmann machines, RBMs, were introduced to simplify training by limiting connections between neurons and making sampling more efficient. Another critical factor in training is parameter tuning. The learning rate, number of iterations, and initialization of weights all affect how well a Boltzmann machine learns. Too high a learning rate can cause the model to diverge, while too low a learning rate can make training unbearably slow. Proper initialization of weights helps prevent the model from getting stuck in poor local minima, improving overall training stability. Despite these challenges, Boltzmann machines remain an important part of machine learning history, and researchers are constantly looking for ways to improve their training efficiency. Some recent approaches include parallelized sampling, better initialization techniques, and even leveraging quantum computing to speed up calculations. These advances could help overcome the computational limitations that have held Boltzmann machines back. With a solid understanding of how Boltzmann machines are trained, the next big question is how they fit into the broader category of energy-based models. Because while they are powerful, they are just one example of a larger class of machine learning techniques that use energy functions to learn from data. Let's take a look at how Boltzmann machines compare to other energy-based models and why this framework continues to influence modern AI research. Boltzmann machines belong to a broader class of energy-based models, EBMs, a powerful category of machine learning algorithms that define probabilities over data using an energy function. These models don't just process inputs and spit out predictions like traditional neural networks. Instead, they assign an energy level to each possible state of the system and learn by minimizing that energy, allowing them to discover deep underlying patterns in data. The core idea behind energy-based models is simple. Lower energy states are more likely to occur, while higher energy states are less probable. This principle, borrowed from statistical mechanics, allows EBMs to model complex relationships between variables, making them particularly useful for unsupervised learning, generative modeling, and feature extraction. Instead of explicitly learning a function that maps inputs to outputs, they focus on understanding the structure of the data itself. Boltzmann machines are one of the most well-known energy-based models, but they are not the only ones. Another popular type of EBM is the Hopfield network, which also uses an energy function to store and retrieve patterns. While Hopfield networks were some of the earliest neural networks developed, they have largely been replaced by more advanced models like Boltzmann machines and Restricted Boltzmann Machines, RBMs, which introduced better ways to learn probability distributions. Compared to other deep learning models, energy-based models offer a few unique advantages. First, they excel at learning deep representations in an unsupervised way, making them ideal for discovering hidden features in data. Second, they are naturally suited for probabilistic modeling, which means they can handle uncertainty better than traditional neural networks. This makes them valuable in applications like image recognition, reinforcement learning, and scientific simulations, where understanding probabilities is essential. However, EBMs, particularly Boltzmann machines, have major challenges as well. Because they rely on stochastic sampling to update their weights, training them can be slow and computationally expensive. While techniques like contrastive divergence have improved efficiency, they are still less scalable than deep learning architectures like convolutional neural networks, CNNs, or transformers. One of the most exciting areas of research today is how energy-based models can be combined with modern deep learning techniques. Some researchers are exploring hybrid architectures where energy-based models are used alongside deep neural networks to improve generative modeling and representation learning. Others are investigating how energy-based models can be adapted for quantum computing, where their probabilistic nature aligns well with quantum mechanics. Despite their challenges, energy-based models, including Boltzmann machines, continue to influence modern AI research. While they may not always be the first choice for large-scale applications, their unique ability to model probabilities, uncertainty, and hidden structures ensures they remain relevant in areas where deep learning alone might not be enough. With this broader perspective on energy-based models, it's time to zoom back in on a special type of Boltzmann machine that helped shape deep learning: restricted Boltzmann machines, RBMs. These simplified versions of Boltzmann machines overcame many of the original challenges and played a major role in the rise of deep learning. Let's take a closer look at what makes RBMs different and why they became so influential. Restricted Boltzmann machines, RBMs, are a special type of Boltzmann machine that were designed to make training more efficient and scalable. Unlike standard Boltzmann machines, which allow every neuron to be connected to every other neuron, RBMs introduce a key restriction: neurons within the same layer cannot be connected to each other. This simple change dramatically improves their ability to learn and has made RBMs one of the most influential architectures in deep learning. RBMs consist of two layers: a visible layer, which represents the input data, and a hidden layer, which learns abstract features from the data. The absence of connections within each layer forces the network to learn structured representations, making training much more efficient. This restriction eliminates the complex looping interactions that make training standard Boltzmann machines so slow, allowing RBMs to use simpler and faster optimization techniques like contrastive divergence. One of the reasons RBMs became so important is their ability to act as feature detectors. Instead of simply mapping inputs to outputs, they learn meaningful patterns in the data by capturing dependencies between different variables. This makes them particularly useful for dimensionality reduction, feature learning, and data representation. For example, in image recognition, RBMs can automatically discover lower-level features like edges and textures before passing them on to deeper layers for more complex understanding. RBMs gained widespread attention when Geoffrey Hinton and his team used them to develop Deep Belief Networks, DBNs, one of the first successful deep learning architectures. By stacking multiple RBMs on top of each other and training them layer by layer, DBNs were able to learn hierarchical representations of data, paving the way for modern deep learning models. This breakthrough helped reignite interest in neural networks and set the stage for the rise of deep learning in the 2010s. Despite their success, RBMs are not without limitations. One of the biggest challenges is that they still rely on stochastic sampling, which, while more efficient than full Boltzmann machines, can still be computationally demanding compared to newer deep learning models. Over time, RBMs were largely replaced by autoencoders and deep neural networks, which offered better scalability and performance on large datasets. However, their impact on deep learning remains significant, and they are still used in specialized applications such as collaborative filtering, anomaly detection, and generative modeling. While RBMs helped bridge the gap between Boltzmann machines and deep learning, they also laid the groundwork for even more powerful architectures, like deep belief networks, DBNs. These networks expanded on RBMs to create some of the earliest deep learning models capable of unsupervised feature learning. In the next section, we'll explore how DBNs work, why they were groundbreaking, and how they influence the evolution of modern AI. Deep belief networks, DBNs, represent a major milestone in the evolution of deep learning, building on the foundation laid by restricted Boltzmann machines, RBMs, to create powerful, multi-layered models. Before DBNs, training deep neural networks was notoriously difficult due to problems like vanishing gradients and computational inefficiency. But with DBNs, researchers found a way to train deep architectures layer by layer, making deep learning more practical and accessible. A DBN is essentially a stack of RBMs where each layer learns progressively more abstract representations of the data. The training process happens in two main stages. First, each RBM is trained independently in an unsupervised manner, learning the hidden features of the data layer by layer. Once all layers have been pre-trained, the network undergoes fine-tuning using backpropagation to optimize for specific tasks, such as classification or prediction. This two-step process significantly improves learning efficiency and allows the model to extract deep, hierarchical features from complex data sets. What made DBNs groundbreaking was their ability to perform unsupervised pre-training. In traditional deep learning, neural networks require massive amounts of labeled data, which can be costly and time-consuming to obtain. DBNs, on the other hand, excel at learning without labels, making them ideal for tasks like feature extraction, anomaly detection, and dimensionality reduction. This ability helped researchers achieve better performance in fields like speech recognition, image processing, and recommendation systems. DBNs played a crucial role in reviving interest in deep learning, with Geoffrey Hinton's work in 2006 demonstrating how they could outperform traditional machine learning algorithms on several benchmarks. This sparked a wave of new research into deep architectures, eventually leading to the development of deep neural networks, convolutional networks, CNNs, and transformers. While DBNs were eventually overshadowed by more scalable models like autoencoders and modern deep learning frameworks, they provided key insights that shaped the deep learning revolution. Even today, DBNs remain useful in certain applications, especially where unsupervised learning is needed or where labeled data is limited. They are still explored in generative modeling, reinforcement learning, and scientific research, where probabilistic models can offer advantages over deterministic deep networks. While DBNs were a stepping stone to more advanced architectures, they also highlighted some of the core challenges in training energy-based models, particularly in balancing efficiency with accuracy. To improve training, researchers refined techniques like contrastive divergence and developed algorithms like the contrastive divergence algorithm, which became essential in optimizing RBMs and DBNs. In the next section, we'll break down how this algorithm works and why it was a game changer in training Boltzmann-based models. The contrastive divergence CD algorithm is one of the most important breakthroughs in training Boltzmann machines, particularly restricted Boltzmann machines, RBMs, and deep belief networks, DBNs. Before CD, training these models was extremely slow and computationally expensive due to their reliance on Gibbs sampling, which required running for an impractically large number of iterations. Contrastive divergence provided an efficient alternative, making unsupervised learning with energy-based models feasible. At its core, contrastive divergence is an approximate learning algorithm that speeds up the process of adjusting weights in a Boltzmann machine. Instead of running full Markov chain Monte Carlo, MCMC sampling, which requires the system to reach thermal equilibrium, CD uses a shortcut. It performs only a few iterations of Gibbs sampling before updating the weights. This drastically reduces training time while still capturing meaningful patterns in the data. The training process in contrastive divergence involves three key steps: initialization, the positive phase, and the negative phase. First, the network is initialized with random weights. In the positive phase, real training data is presented to the model and neuron activations are recorded. The model strengthens connections between neurons that frequently activate together. In the negative phase, the network generates a reconstruction of the data by performing a few steps of Gibbs sampling. The model then compares the generated data to the real input and updates its weights to make future reconstructions more accurate. This process is repeated iteratively, allowing the model to refine its understanding of the data distribution. One of the major advantages of contrastive divergence is that it enables efficient unsupervised learning, making RBMs and DBNs effective for feature extraction, generative modeling, and pre-training deep networks. In fact, the success of DBNs in early deep learning research was largely due to their ability to leverage CD for layer-wise training, overcoming many of the challenges that made training deep networks difficult before 2006. However, contrastive divergence is not perfect. Because it approximates the true probability distribution using only a few sampling steps, it can sometimes introduce biases, leading to suboptimal learning in certain cases. To address this, researchers developed persistent contrastive divergence, PCD, which keeps track of samples across multiple training iterations, improving the stability of learning. Other refinements, like parallelized sampling and hybrid training methods, have further improved the efficiency of training energy-based models. Despite these limitations, contrastive divergence remains one of the foundational techniques in training RBMs and DBNs. It paved the way for early deep learning advancements and continues to be studied in fields like probabilistic modeling and generative AI. Now that we understand how contrastive divergence optimizes Boltzmann machines, let's explore how these models have been applied in image recognition, one of the key areas where their ability to learn deep structured representations has been put to the test. One of the most exciting applications of Boltzmann machines, especially restricted Boltzmann machines, RBMs, and deep belief networks, DBNs, has been in image recognition. These models excel at learning deep structured representations from visual data, making them valuable for tasks like feature extraction, object classification, and facial recognition. Before convolutional neural networks, CNNs, became the dominant approach, Boltzmann-based models played a crucial role in pushing the boundaries of machine learning in vision tasks. The key reason Boltzmann machines work well in image recognition is their ability to learn hierarchical features. Instead of relying on handcrafted image features such as edges, textures, or shapes, these models automatically discover patterns by adjusting the weights of their connections. The hidden layers in an RBM or DBN act as feature detectors, capturing increasingly complex representations of an image. Early layers learn simple patterns like edges and corners, while deeper layers capture more abstract features like object parts and structures. In a typical image classification pipeline, an RBM can be used as a pre-training step, learning important visual features from raw images. The learned features can then be fed into a classifier, such as a support vector machine, SVM, or a fully connected neural network to perform final predictions. This approach was particularly useful in the early days of deep learning, helping models achieve better accuracy on tasks like handwritten digit recognition, MNIST, and object detection before CNNs took over. In a typical image classification pipeline, an RBM can be used as a pre-training step, learning important visual features from raw images. The learned features can then be fed into a classifier, such as a support vector machine, SVM, or a fully connected neural network to perform final predictions. This approach was particularly useful in the early days of deep learning, helping models achieve better accuracy on tasks like handwritten digit recognition, MNIST, and object detection before CNNs took over. Another important application of Boltzmann machines in vision is feature extraction for dimensionality reduction. Instead of using techniques like principal component analysis, PCA, an RBM can learn low-dimensional representations of high-resolution images, preserving the most important features while reducing computational complexity. This is useful in cases where storage and processing power are limited, such as mobile devices or embedded systems. Boltzmann-based models have also been explored in facial recognition, where they can learn identity-specific features from training images and then compare new faces against known identities. Although CNN-based architectures like FaceNet and VGGFace have surpassed them in performance, RBMs and DBNs laid the groundwork for modern deep learning-based face recognition systems. Despite their contributions to image recognition, Boltzmann machines have largely been replaced by CNNs, transformers, and deep autoencoders, which offer better scalability and computational efficiency. However, research into hybrid models, combining energy-based learning with convolutional layers, is still ongoing, showing potential for future advancements in AI-powered vision systems. Now that we've seen how Boltzmann machines have been applied to images, let's shift our focus to another fascinating area, natural language processing, NLP. While not as common as transformers today, Boltzmann-based models have been explored for text generation, language modeling, and machine translation. Let's dive into their impact on NLP next. Boltzmann machines, particularly restricted Boltzmann machines, RBMs, and deep belief networks, DBNs, have also been explored in natural language processing, NLP, a field where understanding complex relationships between words and context is crucial. While modern NLP is dominated by transformer-based architectures like GPT and BERT, Boltzmann-based models played an important role in early deep learning approaches to text generation, language modeling, and word embeddings. One of the key strengths of Boltzmann machines in NLP is their ability to learn probabilistic representations of text data. Unlike traditional rule-based systems, they don't just memorize word sequences. Instead, they learn the underlying statistical structure of a language. This allows them to generate coherent and contextually relevant text, making them useful in applications like automated content creation, text completion, and conversational AI. A major application of RBMs in NLP has been in word embeddings, where words are represented as vectors in a continuous space based on their relationships with other words, similar to how Word2Vec and Glove learn embeddings from large text corpora. RBMs have been used to capture semantic meaning and syntactic relationships between words. This approach helps improve machine translation, sentiment analysis, and information retrieval by representing words in a way that reflects their real-world usage. Boltzmann machines have also been used in language modeling, where they predict the likelihood of a given word sequence. By training on large datasets, they can learn to generate text that mimics human writing, making them useful for tasks like AI-generated poetry, dialogue systems, and text summarization. However, because training Boltzmann-based models is computationally expensive, they have largely been replaced by recurrent neural networks, RNNs, long short-term memory networks, LSTMs, and transformers, which scale better and learn faster. Despite being overshadowed by newer architectures, the unsupervised learning capabilities of Boltzmann machines still make them valuable in some NLP applications, especially where labeled data is scarce. In areas like topic modeling and document clustering, they can uncover hidden structures in texts, making them useful for automatic categorization of news articles, research papers, and customer reviews. While they may not be the leading choice for NLP today, the principles behind Boltzmann machines, energy-based learning, and probabilistic reasoning continue to influence advancements in AI-driven text generation. Some researchers are exploring hybrid models that combine Boltzmann machines with deep learning techniques to improve efficiency and scalability in NLP tasks. Now that we've seen their role in NLP, let's move on to another critical application: recommendation systems. Here, Boltzmann machines have been used to predict user preferences, improve content personalization, and enhance online shopping and streaming platforms. Let's explore how they have shaped this space next. Boltzmann machines have played a significant role in recommendation systems, helping platforms like Netflix, Amazon, and Spotify predict user preferences and personalize content. While deep learning has taken over much of the recommendation space, Boltzmann-based models, particularly restricted Boltzmann machines, RBMs, were among the first successful neural network approaches used for collaborative filtering and content suggestion. At the core of any recommendation system is the ability to predict what a user will like based on their past interactions. Traditional methods like matrix factorization, e.g., singular value decomposition, SVD, focus on finding relationships between users and items, but they often struggle with sparse data sets where users have only rated a few items. This is where RBMs prove to be highly effective. They could uncover latent patterns in user behavior by learning probabilistic relationships between users and the products, movies, or songs they engaged with. In an RBM-based recommendation system, the visible layer represents user-item interactions, such as movie ratings, and the hidden layer learns deeper representations of user preferences. By training the model on existing user data, it can infer missing ratings and predict which items a user is likely to enjoy. Unlike traditional collaborative filtering methods, RBMs can capture nonlinear relationships between users and items, improving the quality of recommendations. One of the key advantages of using RBMs in recommendation systems is their ability to handle sparse data efficiently. In many real-world scenarios, users only interact with a small fraction of the available items, making it difficult for traditional models to generalize. RBMs mitigate this by learning meaningful features from limited interactions, making them particularly useful for personalized content recommendations in e-commerce, video streaming, and music platforms. Boltzmann-based models have also been explored for personalized recommendations beyond user ratings. By incorporating additional information such as browsing history, purchase behavior, and contextual data, these models can refine predictions and provide more accurate, tailored suggestions. This approach has been used in fields like news recommendation, online learning platforms, and targeted advertising. Despite their strengths, RBMs and other Boltzmann-based models have been largely replaced by deep learning techniques like neural collaborative filtering (NCF), autoencoders, and graph-based recommendation algorithms. These newer models scale better with large datasets and benefit from advancements in GPU acceleration, making them more practical for modern large-scale recommendation systems. However, the legacy of Boltzmann machines in recommendation systems remains. They were one of the first neural network-driven approaches to personalization, influencing the development of more advanced deep learning-based recommendation algorithms. Some researchers are even revisiting hybrid models that combine RBMs with deep neural networks to improve accuracy and efficiency in personalized content delivery. With their impact on recommendation systems explored, let's look at where Boltzmann machines are heading in the future. Are they a fading part of AI history, or could they make a comeback with new advancements in technology? Let's explore what's next in the world of Boltzmann machines. As machine learning and AI continue to evolve, the future of Boltzmann machines remains an open question. While they have been overshadowed by deep learning architectures like transformers and convolutional neural networks, there are still exciting research directions that could bring them back into relevance. With advancements in computing power, hybrid architectures, and quantum computing, Boltzmann machines might yet find a place in the next generation of AI systems. One of the most promising areas for their resurgence is unsupervised learning. While most modern deep learning models rely heavily on labeled data, Boltzmann machines are fundamentally probabilistic generative models, meaning they can discover hidden patterns in data without needing explicit supervision. As the demand for AI systems that can self-learn from unstructured data grows, researchers are exploring ways to improve the scalability and efficiency of Boltzmann machines for tasks like anomaly detection, feature learning, and probabilistic reasoning. Another exciting direction is the integration of Boltzmann machines with deep learning architectures. Hybrid models that combine energy-based learning with deep neural networks could offer the best of both worlds, leveraging the generative power of Boltzmann machines while benefiting from the efficiency and scalability of deep learning. Some studies are already looking at how restricted Boltzmann machines, or RBMs, can be used for pre-training deep networks or improving generative modeling in tasks like image synthesis and reinforcement learning. Perhaps the most groundbreaking opportunity for Boltzmann machines lies in quantum computing, because Boltzmann machines are naturally based on probabilistic models. They align well with the principles of quantum mechanics. Some researchers believe that quantum Boltzmann machines, QBMs, could leverage the power of quantum computing to perform parallel computations on an unprecedented scale. This could dramatically reduce training time, overcoming one of the biggest limitations of classical Boltzmann machines. If successful, QBMs could play a major role in fields like quantum AI, scientific simulations, and high-dimensional data modeling. Beyond quantum computing, Boltzmann machines also hold potential in scientific and medical research. Their ability to model complex probability distributions makes them suitable for applications in genomic data analysis, drug discovery, and climate modeling, where understanding intricate relationships in large data sets is critical. That said, Boltzmann machines still face major hurdles before they can become widely adopted again. Their training complexity and computational inefficiency remain significant challenges, and deep learning models continue to dominate the AI landscape. Unless major breakthroughs in optimization algorithms or hardware acceleration are made, Boltzmann machines may remain more of a research curiosity than a practical tool in mainstream AI development. So, what does all this mean? Are Boltzmann machines a forgotten relic, or could they still shape the future of AI? While they may not be at the forefront of deep learning today, their core principles of energy-based learning and probabilistic modeling continue to influence machine learning research. If advances in hybrid architectures, unsupervised learning, or quantum AI prove successful, we might just see a Boltzmann machine renaissance in the coming years. As we wrap up our exploration of Boltzmann machines, let's take a moment to reflect on their key contributions to machine learning and what we can learn from their successes and challenges. Let's move on to the final conclusion. As we reach the end of our exploration of Boltzmann machines, one thing is clear. These models have played a crucial role in shaping the evolution of machine learning, even if they are no longer at the forefront of AI development. From their origins in probabilistic learning and energy-based modeling to their impact on deep learning, recommendation systems, and generative models, Boltzmann machines have left an undeniable mark on the field. One of their biggest contributions was their role in unsupervised learning and feature discovery. Long before deep learning took over, restricted Boltzmann machines, RBMs, and deep belief networks, DBNs, were some of the earliest architectures capable of learning deep hierarchical representations. They showed that neural networks could self-learn patterns in data without needing explicit labels, influencing the development of modern autoencoders, GANs, and transformer-based models. Another key takeaway is that Boltzmann machines demonstrated the power of probabilistic reasoning in AI. Unlike traditional neural networks, which focus purely on classification or regression, Boltzmann machines modeled probability distributions, making them effective for generative modeling, anomaly detection, and data reconstruction. This principle of energy-based learning continues to inspire AI researchers today, particularly in fields like Bayesian deep learning and uncertainty modeling. However, Boltzmann machines also highlighted key challenges in AI research, particularly in the areas of training efficiency, scalability, and computational cost. Their reliance on stochastic sampling made them impractical for large-scale applications, and as deep learning architectures improved, they were largely replaced by faster and more scalable models. While they pioneered many of the ideas that deep learning relies on today, their full potential was never fully realized due to hardware and optimization limitations. That said, Boltzmann machines are not entirely obsolete. New research directions, such as hybrid models combining energy-based learning with deep neural networks, advances in contrastive divergence optimization, and the rise of quantum Boltzmann machines, QBMs, suggest that they could still have a role to play in the future of AI. If these challenges can be overcome, Boltzmann machines could see a resurgence in unsupervised learning, scientific computing, and quantum AI applications. So, where do we go from here? The story of Boltzmann machines is not just about one model, it's about the evolution of AI itself. As new technologies emerge and machine learning continues to advance, some of the core ideas behind Boltzmann machines, probabilistic reasoning, energy-based learning, and unsupervised feature discovery, may still shape the next generation of AI breakthroughs. Whether they remain a foundational chapter in AI history or make a comeback with new advancements, Boltzmann machines have already changed the way we think about learning, decision-making, and data representation. Their impact is woven into the fabric of modern machine learning, and their influence will continue to be felt for years to come. With that, we conclude our journey into Boltzmann machines. I hope this exploration has given you a deeper appreciation of their strengths, weaknesses, and potential future applications. As AI continues to evolve, who knows? Maybe one day we'll see Boltzmann machines return in a way we never expected.